Yeah, thank you very much, Timo, and thanks a lot for the invitation. I'm very honored to be part of this amazing list of speakers. So, yeah, and I'm very happy to show you some work we did and also give you. So, first, want to start with a short introduction to neural networks. But I will cover it more from a mixed integer programming perspective, which you should be familiar now after the first week of the workshop. So there's another tutorial in the afternoon, which goes more into the real deep learning, how to train these models and so on. But I'm interested in the mixed integer perspective on this and how can I use these neural networks in robust optimization. So this will be the second part. And then hopefully, it's very ambitious, I can get to the end and show you also how to construct uncertainty sets for robust optimization again by using neural networks. So first, what is a neural network? So you normally see these pictures. So the idea is it's based somehow on the human brain. So what you have is like an input layer. This is the data space you can imagine. So a pictures or whatever data you have. Then you have these hidden layers. So each column is one layer. Each circle is normally called a neuron. And you have these this is called a fully connected network. So you have all these connections between each neurons. The idea is like in the human brain, like the information is processed from neuron to neuron, and the neuron is either activated or not activated. I will come back to that in a minute. And then you have the output layer. This is basically the output of your what your neural network is predicting or classifying. So mathematically, how does it look like? Mathematically, the neural network is just a concatenation. So it's a function which maps data point x into a value in another space. And it's basically concatenation of functions. So each function is one layer of the neural network. And each of the functions is very simple. It's just a linear function. So you have a weight matrix W, what's called a bias B. So that's just the constant vector here. And you're mapping the input of the layer. So that is what gets into the layer. You just have a fine linear transformation of it. And then you apply what's called an activation function. So you can choose different functions here. One very popular choice is the ReLU, which is just the maximum of the value which comes in and zero. So if it's negative, then the neuron is deactivated. So the value which comes out of the neuron is zero. If it's positive, then just the value goes through. So that's the idea here. And then, yeah, you can again picture this in this way. So each layer basically has a weight matrix W and a bias B, which are the values which we have to train during the training process. So we don't know these values. So already we saw some introduction in the first talk. So what is actually such a regression model doing? So the very easy idea for which you probably know is linear regression or polynomial regression. So what you're doing in these regression models, basically fitting a function to the data points. So you see here, for example, to fit a polynomial to these data points. What you need for this is you need some training data. So you have a list of training data where X is the input space and Y is actually the outcome, so the value you want to predict. So you need a certain set of data, and then you can fit a function by minimizing an error, as we saw in the first talk, such that this approximates well the true distribution or the true behavior of the data. And in deep learning, you're doing exactly this, but your function is now a neural network. So you have to define your structure. So your neural network has a certain amount of layers and neurons, so you have to fix that. Then you have to define a loss function. This can be the squared loss or logistic loss or whatever. Normally, you use what's called a regularizer, which is to ensure that during the training process, the weights behave well. And then you're solving this optimization problem, which we also saw in the first talk. So you're minimizing a loss. what you see here is the outcome of your neural network. So the W and the B means these are the weights of the neural network which you try to find. So you're optimizing over W and B. And you want that your loss of what your neural network is predicting and the true outcome on your data, should be small, right? So you're minimizing this loss here. And then you have this regularizer, which you can use the square, the 2 norm or the 1 norm. These are popular choices. This just controls that these weights here are behaving well, and you get, and it's can be observed that this leads to better prediction values. So as I said, the solution methods for this will be covered in the tutorial this afternoon. I don't go into detail here. Basically, what you often use is stochastic gradient descent methods. So you're minimizing this by a first order method. It's not guaranteed that you find the global optimum. These neural networks are highly non-convex. So you cannot guarantee global optimality, but it works well. And it generalizes well on unseen data. That's actually what you're aiming for. You don't want to find the optimal, the global optimum. You want to behave well on future data, right? So that's the ultimate goal. So why are neural networks so popular? I think there are many reasons. One reason is the expressivity. So there are many works which show actually that you can approximate a lot of functions by neural networks. So there's a nice survey on this where you can find results like this. So every continuous function can actually be approximated by a neural network, of course, up to accuracy of epsilon. So basically, if you don't know what your true function is, but it's continuous, then there is a neural network. It's not clear that you find this neural network, but there is a neural network which can approximate this well. And if you go for piecewise linear functions, we will see later that actually neural networks are piecewise linear. Then every piecewise linear function you can approximate exactly by a real neural network, where the number of layers is at most logarithmically in the data space dimension. Okay, so if you have a piecewise linear function, there is a neural network which can perfectly imitate this function, but still the question is, can you find it? And another success, or why deep learning is so successful, is the backpropagation. You will also see more of this later, I guess. So actually, when you use these gradient methods now, you have to calculate the gradient in each iteration. So this should be a quick operation. And by this way, how the neural network function is defined, so it's a concatenation of functions, you can actually use the chain rule to calculate the gradient of this function. So you go basically from the end backwards through all these functions, through all the layers, to calculate the gradient. That's what's called the backpropagation. And this can be also highly parallelized. So nowadays, with GPU hardware, you can actually do this very, very efficiently. And this is part of why this works so well, because you have huge networks. You need huge networks at some point to approximate or to get good predictions. And then you have to calculate these gradients very efficiently. So that's why this backpropagation is a nice feature you can use here. Good. So then I already mentioned it a bit. So what you can actually think about, and this is a nice intuition which came from me with this paper, but there are a lot of other works nowadays about this. So actually, these neural networks look very complicated functions, highly nonlinear, non-convex, but actually it's just a piecewise linear function. And I will just guide you through how to see this. So what you can actually do is you can fix an activation pattern of the neuron. So you go through every neuron, you say this is activated, this is not activated, whatever. You just fix it in a certain way. Now every data point which fulfills these activation patterns is actually contained in one of these polyhedron here. And you can see that because you have a ReLO activation function. So when it's deactivated, this means what's getting into the ReLO must be lower or equal to 0. If it's activated, it must be larger than 0, right? So the weights of the trained neural network you already know. Let's assume this. Now this means that every neuron gives you actually a linear constraint in your data space, right? So if it's activated, it's a linear constraint like this. If it's deactivated, it's like this. So in each of these spaces here, a data point has the same activation of the first layer. Now you have to go over through the second layer. Now again, in each of the regions, you get again through all these activations of the second layer, you get these linear functions and so on. And then actually what you do is you're partitioning your data space into these polyhedral regions. And now in each region, when all the activations are fixed, the neural network doesn't have these non-linearities anymore. So remember, every function is a linear, fine linear function. So the only non-linearity comes from these activation functions, which is the ReLO. Now, if you fixed all these ReLO, like the activations, then everything is linear. So on each of these subspaces here, you have a linear function in the end, or a fine linear. And if you combine this, then this is just piecewise affine. Okay, that's the high-level idea. So here's an example. So assume you have this neural network, you can only partly see. So you have the weights already. So we assume this network is trained. So this is very easy one. You only have the data space has 2 dimensions, and you have one hidden layer with 2 neurons, which is here and here. And then it's one output value. So you can write it in the mathematical formulation like this. So this is the first weight matrix. So this W1. You apply your data point here, then you apply one activation function on each of the, by the way, I didn't mention this, this is component-wise. So for each component, you're applying this ReLO function. And then you have your second layer matrix, which is just a vector. And now what you can do is you can just fix one activation pattern. So activation pattern means now let's go for the hidden layer. This neuron is deactivated, this neuron is activated. So what does that mean? That means what's coming into this neuron must be smaller or equal to 0, because then the ReLO is deactivated. So this gives you this constraint here, right? You take the first row times x1, x2. This must be lower or equal to 0. Now you go for the second neuron. This is activated, so here it must be greater than 0. So here you get another constraint. So what you actually see is all the data points x1, x2, which fulfill this activation pattern, are lying in this region here. Okay, so it's below this line, above this line. So this is all the data points which fulfill the activation pattern. And now if you just check what is the outcome now for this activation pattern of my neural network, then you know, okay, you have to multiply what's getting out of this ReLO here with the second layer. So 0.5 times 0, because the first layer is always deactivated. This is always 0, plus 4.2 times what's getting out of the second layer. And this is actually this here, because it just passes through the ReLO. And this means 4.2 times this. So this is a linear function in X. Right? So basically what you're showed here, if you fix this activation pattern, then every point in this region fulfills it, and the outcome of the neural network is a linear function in these values. Okay? And now you do it for all activation patterns. Oh, shit, you cannot see it. Sorry, so actually what I want to show you here is, so this is one activation pattern, what we saw. Here you have another activation pattern in this region. In this region you have another activation pattern, and here you have another one. Okay, so these are all 4 activation patterns, and for each one you have a linear function, and then in the end this is piecewise linear. So just to, I hope everyone is believing me now. So you can also see, if you want to get a nice introduction to this, you can check this paper, which is very nice. It's considering the geometry of deep learning. So they have also very nice pictures there, what you see here. So that's exactly what I showed you, but in a 3D example now. So the data space is actually clustered into these polyhedral areas. In each polyhedral area, you have one activation pattern. And then your function, the output of your neural network is just linear on each of these, a fine linear on each of these parts, right? So then it looks something like this. So this is good. We know that neural networks are piecewise linear. Why is this good? So if you're coming from mixed integer programming, you realize that, so if you hear a piecewise linear function, you know you can model it with a mixed integer program. And the idea is very, I mean, it's not easy, but it's, let's say, basic in when you're a bit experienced in mixed integer programming. So again, let's say, how can we model this? This is our first layer. We're applying our matrix with X, and each time we're applying the activation function. So let's take one of these neurons again. So how can you model one neuron? You have to somehow, so everything here is linear, that's good, but you have to model the max of Z and 0. That's the ReLU activation. That's what's coming out of the first layer. So let's call this V. V is what getting out of the first neuron of the first layer. And now actually what you can do is you can model this max of Z and 0 by so-called big M constraints, which look like this. So these are the constraints just for one neuron. So what they are doing is actually you have a 0, 1 variable which decides is the neuron activated or not. If it's 1, that means it's activated. You can see here, if you apply 1 here, then this must be 0. Sorry, it's the other way around. 1 means deactivated. So if you put a 1 here, then this is 0, this is 0. So this means the V, what is the outcome, must be 0. That's exactly what happens when it's deactivated. And the other constraints are not violated, because in this case, what's coming in must be lower or equal to 0. That's when the ReLU is 0. If you take the other case, if U is 0, then you see here this term gets 0. So actually now you have W transpose X lower equal V and greater equal V, so it must be equal to V. This means that actually exactly the neuron is activated, so the W transpose X goes through. And the other constraints are not violated in this case because you have these big M's here. Big M is just a very large value which, such that these constraints are not violated. Okay. So this is the way to model one neuron. You have to do it, of course, for all the neurons. So that blows up quite much. But at least you can say that every neural network with ReLU activation function, if you want to just optimize over this neural network, which is already trained, by the way, so we know all the weights and all the biases, then you can model it as a mixed integer program. So this was already seen in 2018 by Fischetti and Yo, and now I think many people are using it. So this is quite nice. So you can optimize over neural networks. And there are a lot of works actually where they try to improve this optimization because still these big M constraints are very hard. You have a lot of neurons, so you have a lot of these big M constraints. You have a lot of variables. So this is still a very hard problem to solve. But there are a lot of works who try to improve it. So you can do progressive bound tightening, lossless compression of neural networks, so somehow shrinking these neural networks. And there are nice works already where they connect. So this is a nice survey here where they actually connect the deep learning with the polyhedral theory, which is also connected to what I just showed you. Okay, now why do we need that? I will show you in the second part of the talk to how we can use this mixed integer program perspective in robust optimization. But there are many other applications, and they're even coming more and more now since people using it in the optimization world. So for example, adversarial examples is one thing you can use it for. So an adversarial example is basically find for a data point a very close data point, so you're minimizing the distance, such that the outcome of your neural network is vastly different. So you're trying to find a very close point where the outcome of your network is very, very different. These are these examples where you have pictures and you just, it's classified correctly as a panda, but you just change some of the pixels of the picture, so the human still sees there's a panda, but the network completely misclassifies the picture. So these are, that's why you want to have these examples. It's kind of a way to fool your neural network, and it can improve the neural network prediction. So what you need here is you need to optimize over this. You have to model this here. So you can model it as a mixed integer program. The same for counterfactual explanations. That's a very similar concept to adversarial examples. You can do robustness analysis, so you can ask what is the maximum radius in my data space around a point such that my network does not change the classification. You can prune neural networks, so you can try to remove a lot of neurons such that the outcome, the prediction is still the same. So that's you can do by mixed integer programming nowadays. You can even train binarized neural networks, not real neural networks, but if the weights of these matrices are only -1, 0, or 1, then you can actually use these MIP ideas to train even the network. And there's some new works on constraint learning. So if you have optimization problems with difficult constraints in the sense that you cannot model them. So for example, if you optimize a food basket, then you want to have a food basket which is palatable. So how can you model palatability in math formula? So that's very difficult. So what you can do is you can train a neural network which predicts if a basket is palatable or not. And then you can model this neural network into your optimization problem, and can optimize over it. Okay, this was a very short introduction to the deep learning part. If there are no questions, I can go over now how to use this idea in robust optimization. So I don't go too detailed in robust optimization, but I think the main concept you can grasp from what I show you. So first, the motivation for it. So we're back into the optimization world now. So there are many applications where uncertainty appears in your problem. And one example is the facility location problem. So what you're doing here is you have two decisions. You have a lot of possible locations for your warehouses, let's say, and you have a lot of customers. These are the circles. And in the first stage, that's what you have to do here and now, is you have to decide which of the facilities do I open. So you have to decide, okay, this one, and this one I open. So this comes with a cost, of course, and this is a long-term decision. But at this point, you don't know the demands of your customer. So each of these customers has a certain demand, what you have to serve them from your warehouses. So now at some point the demands are known, so your customers have to tell you how much they need. And now in the second stage, after you know these demands, you can actually now say, okay, which customer do I serve from which facility? So this is the decision you can do in the second stage. So you have basically a problem where you have the first stage decisions and the second stage decisions. And there's a lot of uncertainty here because transportation can be uncertain, but especially the demands of your customers can change over time. So right now you have to build your facilities, so you can you have to decide now where you do it, and you don't know the demands. So these are two-stage. You can tackle these problems with two-stage robust optimization. So let me try to get you into the problem. At some point, you have to look very long at this problem to get what's happening there. But the idea in robust optimization is you have an uncertainty set. That's what you see here. And you're always optimizing for the worst case. So you want to find a solution which is worst case optimal. So what you're doing here, this is the first stage. So these are the X variables are the decisions you're doing the first stage. This is opening the facilities. Then what you're considering is now the worst objective value over all scenarios in your uncertainty set. So the size are the uncertain parameters. So these could be the demands in the facility location problem. Now, so for the worst demand realization, you can imagine you are now trying to find the best costs. So these is your objective. These are the costs. But what you can do is still you have the second stage decisions. So these decisions you can do after the uncertainty realizes, right? So these Ys in this case would be the assignment of the customers to the facilities. So you can do this after the uncertainty is known. So that's why the minimum here comes after the maximum. So for every Xi here, for every demand realization, you can choose the best allocation of the customers. And this, you have to model, okay, you have an objective function and you have constraints. In your constraints, the X can appear, and of course the Xi, the uncertainty appears. Okay, so somehow I hope it's clear what we're doing here. So we have these min, max, min problems in two-stage robust optimization. And these are extremely hard to solve, especially, so there's a lot of work on this when the variables are continuous. That's unfortunately not the case in the facility location example. And this problem gets very, very hard when the variables are integer, especially the second stage variables y, and if the uncertain parameters appear also in the constraints. That's what you see here. So the Xi is influencing the constraints of this problem. So there is one way, so there are not many ways to solve this kind of problems. There's one way which is called column and constraint generation. So I think you're now after this week familiar with constraint generation. Column and constraint generation is just you're generating constraints, but also variables at the same time. And so again, this is a bit of, you have to quietly think this through, but what you see here actually is this min-max-min problem, what we saw before, but with a finite uncertainty set. So we are replacing our uncertainty set, which can be a convex set with infinite many scenarios. We are replacing it with a finite set. So we are just having, let's say, 5 scenarios in there for now. So what you're doing here is actually you just do a level set transformation. So this is modeling the maximum over all of your objective function over all scenarios. And now we have the second stage. So these Ys, so for each scenario, we can react with a different variable Y, right? So this can be different for every scenario. So what we're doing here is we're introducing a copy of these Y variables for every scenario. So for every scenario, this is only a finite number now. We have a different second stage reaction here. And that's what you see here. So for every scenario, you can choose a different second stage reaction. For every scenario, you choose here the different second stage reaction. And the worst case, this maximum is hidden here because you have a for all constraint here. So this must hold for all scenarios. Okay, it's kind of clear. I know this looks very difficult, so you have to somehow think a bit through this. But believe me, for now, this is just the min-max-min problem with a final set of scenarios. Now we need to model this for all scenarios in the uncertainty set. So what you're doing is you're doing this iterative loop here, where you iteratively add new scenarios to the problem. And you do this by solving the adversarial problem. So for a solution of this problem, let's say X star, mu star is the solution of this main problem. You're trying to find now a scenario which violates your solution. So you're actually solving this inner max-min problem for your given solution. So you're plugging in your X star solution, and you're solving just the inner max-min problem. If this gives you a solution which is cutting off your current mu star here, so this value here is larger than mu star, that's what you see here, then you found a scenario which is violating your constraints, so you're adding it to the main problem. and then you just loop until your adversarial problem says, no, there's no scenario anymore which violates your solution. So this means you're optimal actually, because your solution holds for all scenarios. So the worst case is true, and this means your current solution is optimal. Okay, so this is what you're doing here iteratively. You're just adding new scenarios. You're just increasing this this uncertainty set here until you have a proof of optimality. So this is one of the methods you can use. One of the few methods for now you can use for this problem. Now, still this method is very, very slow in a certain way. So there's a very nice picture from which I stole from this paper here. What they show here is actually what you see here is the percentage of instances you can solve with this column and constraint generation. And what you see is you can solve 80% very, very quickly, but then nothing happens anymore. So there are 80% very easy instances you can solve with this method, but then the method is stuck. And if you apply it, you see there is a certain optimality gap in your branch and bound method, and it doesn't continue anymore. So this is very bad because you never can solve these other 20% of instances, right? So there are some work. So we did some work for objective uncertainty, where the uncertainty only appears in the objective function, then the problem is easier. And there is also works where the uncertainty is in the constraint, but the second stage variables are continuous. That's also an easier case, I would say. There are some promising works on this. And the real hard case where the constraint uncertainty is in the problem and we have integer second stage solutions, there's not really much. There's a general method, which is also not very computationally not very efficient. And there's this nice work of Henri and Martin Schmidt and Johannes, where they use it actually for a specific type of problems, so interdiction type problems. But this doesn't work in the very general case. So what we try to do here is to speed up now this column constraint generation method by using neural networks. And the idea is the following. So you are actually, so that's the main ingredient. You're training a neural network. So this is now a neural network function which predicts the optimal value of the second stage problem. So what you see here is just the second stage problem. So the x is fixed, the psi is fixed. You're just solving one linear problem. It's just the allocation of the assignment of the customers to the facilities. And now your neural network should predict this. So you give a first stage decision, you give a scenario, and the neural network should predict this value, only the optimal value. In this case, now all these are the two problems we have to solve in the column and constraint generation. So these problems get much, much easier now, because you can just replace for every scenario the constraint with the neural network constraint. And remember, we can model neural networks with mixed integer programming formulation. So this here looks easy right now, but this is the whole mixed integer programming formulation of the neural network you have to plug in here. But you see here now for you're optimizing over x. For every x, your neural network for every psi predicts the second stage value, and this is what you're minimizing. So that's now much easier. You don't have this copy of second stage variables anymore, and so on. The same for the adversarial problem. You're just maximizing the second stage value here. So you can just maximize the neural network value here. Again, the neural network is a mixed integer program. So this is a mixed integer program you're solving here. Okay, so this looks much easier. It didn't work very good. This works very good. So one problem was that if you go back here, so this doesn't check the feasibility, and also like there can be a lot of errors in the neural network predictions, right? So what we actually came up with which is I think much smarter and works better, is we don't let the neural network predict the value of the constraints, so the second stage. So we still let it predict the value, but the decision we are doing here is we are using the neural network to decide which of the scenarios we have is actually the worst one. So now if the error is if the neural network has a certain error, it still can predict the worst scenario in many cases, right? So even if there's an error of a certain size, it could be that the worst scenario is the correct one. So what we're doing is we're just using the argmax here, which you can again model. I don't go in detail here. So the neural network decides which is the worst scenario of the ones we have in our finite set. And now we plug this into the constraints. So we are sure we are finding a solution which is feasible, and we plug it into the objective function. So we are actually now optimizing for the real objective function for this scenario and not for the neural network prediction, which could be wrong. So that works much better. Now the question is still, how do we model these neural networks? So there's a very smart idea here, which helps a lot in efficiency. So I told you this whole neural network has to be modeled by a mixed integer program, which can be quite huge. So what we did is actually we have two separate neural networks, which are the embedding networks for the first stage solution X and for the scenarios. So this is a smaller network, but we have two of them to embed the X and the Xi. Now the outcome, we are concatenating it again, and we are sending it to a very small network here. This is actually in the end something like 8 neurons or something. So this is not very huge to get our prediction. So the advantage here is that when you consider the main problem, here the Xi's are actually given in your uncertainty set. So these are already known. So this part here, you don't have to optimize over it. You can just pre-calculate it. So you just send your scenarios through the network, you get the value. You don't need to model this mixed integer program formulation for the red part here. The same in the adversarial, you have your X star already. You don't have to optimize over the X here. So this part, the green part, you can now pre-calculate it. You don't need to optimize over it. So you're saving a lot of constraints and big M constraints and variables. And in the end, this network is quite small. So this can be, by this construction, it can be quite efficient to optimize over it. Still one detail here which you can improve is, for now, if you consider this, now the input size is fixed here, right? The X has a certain size, so the network has a certain input size. This is the problem if you want to solve larger instances in the future. It could be that you want to use your network to solve instances which have many more variables. So this doesn't work here. So what you can use here is a set-based architecture for a neural network. So the idea is actually you have these embedding networks not for the whole vector, but for each component of the vector. So for the first component of the X plus some additional information, which are the coefficients of the problem or whatever, you have one network which predicts the embedding. And you do this now for every component with the same network. So you only have to train one network, and later you can apply it to, even if your dimension increases, you can apply it to larger dimensional X, and the same for Xi. Now this is the small detail here so that you can generalize to larger instances. And now let me skip this and show you the experiment results. So what we did now, we sample first stage solutions and scenarios to train our neural network. So we need data for this neural network. So we sample these from a distribution, and each time we solve the second stage problem, which is quite an efficient, can be done efficiently. So we do this for 500 instances, 10 first stage, 50 scenarios, which comes, so we're coming up with 250,000 data points. Now you can use these very efficient deep learning methods to train your network. Also you can parallelize the data generation and the training process here. And so now you got your network, which is quite good in predicting the second stage values. And now we apply it in the column and constraint generation algorithm. And we compare here. So this is a two-stage knapsack problem where we compare with the algorithm from Aslan and Etienne, which works for objective uncertainty. So this is an objective uncertainty problem. And what you see here is actually, of course, this is an exact method, so it gets the exact optimal solution of the robust problem. So our method is of course a heuristic. We cannot guarantee that our neural network is precise. So our solution is not guaranteed optimal. So we get slight, like around 1% worse solutions for the easy instances. But you see actually the harder the instances get, then we can even find better solutions than the exact solver. So this is the case because the exact solver after the time limit didn't find the optimal solution. And we can actually, so you see here the time limit of 10,000 seconds is hit, while we can find better solutions in up to 30 seconds. So this is very, very fast and it can give very good solutions here. And now this is very ongoing work for the facility location problem where we have constraint uncertainty. And here we actually needed a good baseline, so there are not many good baselines. So this column constraint generation in the exact version doesn't really work here. So we compare against the K-adaptability approach, which is not important right now how it works. It's just a way how to get approximate solutions for the two-stage problem. And you see again, the results are quite good here. So this is very fast. So we can get better solutions. Forget about this column here. You see this is the median error. So we have the better solution, the best known solution compared to the other approximation method, and the run times are still very, very fast. It's just like 20 seconds. Good, let me see if I can get you to the next topic in the last 5 minutes. So just to mention what is the open problems here. I think there's a lot to do here. There's not much yet. So of course you can ask for approximation bounds. That's one slide I skipped. We have an approximation bound, but this is a very conservative one. So the question is, how good are our solutions? Can we actually guarantee that they are certain, have a certain like a certain error compared to the optimal solution? Then of course the constraint uncertainty case is still very hard to solve. So the facility location is constraint uncertainty, but you cannot always guarantee feasibility because you have constraint uncertainty. So there's a lot to do there. And also the question is, can you use neural networks for other algorithms? Can you support other algorithms, which is not very much investigated yet in the robust optimization community? Good. So very quickly, just to show you what you can also do with neural networks here is the construction of the uncertainty set. So for now, I showed you this robust problem and I said, okay, we have an uncertainty set, but actually, how do you construct this uncertainty set? That's a big problem. What you normally have is some observations of your scenarios. So the scenarios in the facility location were the demands, but you could also consider a transportation problem. In this case, the scenarios could be the travel times in a graph. So you can observe this. You can collect a lot of data here. But how do you construct your uncertainty set now? So what is a good uncertainty set you want to hedge against? So there's a lot of work on this. But let me very quickly show how you can use neural networks again here. So the idea is actually to use one class deep learning. So this is not what I showed you at the beginning, is how to predict values based on labeled data. So you have a data point and a label and you're trying to predict these labels. Now you don't have labels. So you just have a set of scenarios, and these are the true scenarios, but you don't have wrong scenarios. So what is the wrong traffic scenario? So what you need is this one class deep learning, which is also called or known under anomaly detection. So this just predicts for every scenario, is it a true scenario or not? Is it an anomaly or is it a real, a true scenario? And the idea is, again, based on neural network transformation. So here's your data space. So these, all the black dots are the real scenarios you observed. And then you have some which are outliers. Now you can apply these to a neural network. The neural network projects it into a different space of a different dimension. And here in this new space, you're trying to map them all to a very close to a point. So you want to map them into a ball with a small radius. So somehow all the black scenarios are mapped into this ball and all the outliers are outside of the ball. And now the neural network tells you everything which ends up in the ball is a true scenario, everything else is an anomaly. And yeah, you can again use these gradient methods to train something like this. So you're training now, you're mapping your data, your scenarios close to a center of the ball. So you're minimizing these norms. Again, you have a regularizer. And then you can define, so if your network is trained, then again, you can define your uncertainty set like this. So you say now all the scenarios which are mapped into this ball are my valid scenarios which are used for robust optimization. Everything outside, I don't care. And now if you look at this set, now again, this is a piecewise linear function. It's can be modeled as a MIP. So this actually gives you a certain structure of uncertainty set. So this is a comparing method where they use support vector machines for this clustering. So you see here the sets are quite bad in many cases because they are always convex. And the neural network, because of this high non-convexity, it can actually find quite good sets where also the regions are non-convex or even disconnected. And now again, you have to solve the robust problem. Yeah, I have to be very quick here. So it's the same idea. We are just considering a classical robust problem here, not a two-stage one. The algorithm for this is easier than this column and constraint generation because you're just generating constraints in this case. But it's the same pipeline. And again, what comes up here is an adversarial problem. You have to optimize over your uncertainty set. Your uncertainty set is now given by the neural network outcome. So again, this can be modeled as a mixed integer problem. And so you can actually solve the robust problem now with this network, with the neural network uncertainty sets. And there's also a nice extension of this by the group of Eric Delage, where they actually now consider conditional robust optimization. So they have some context information like the weather. So you could assume if the weather is different, then the scenarios, your traffic looks different. So you have for different context, you have different scenarios, and now they used our method to construct these uncertainty sets for this case. Yeah, then I would like to finish here. So what I showed you is you can model neural networks which are trained as mixed integer programs. These MIP representations are very useful. So you can implement them in the CCG. For example, you can implement them in many other ways. You can model uncertainty sets by it. And yeah, I would be also very happy to chat if someone has other application ideas or knows anything. Thank you.